Okay, hi. Welcome to the last presentation of MEC 110. So this is the last video. For this last video, I thought I'd talk about, this is kind of an advanced topic. So I'm going to go through it fairly quickly. These slides are only slightly modified from what I present in my graduate course. So excuse me if they're a little bit technical. But I want you to get an idea of what life cycle assessment is, sometimes called life cycle analysis. This is a relatively new, what I would say, technique that's used to evaluate the environmental impacts of a product or to compare the environmental impacts of a product. It's, really within the last couple of decades has become a really useful tool. Oh, and I start this with my favorite Greenberg cartoon. This is one of my real favorites, showing a tree 100 feet tall, being chopped down, converted to paper, getting transported to the retailer as a bag, somebody putting stuff in the bag, and then it gets 100 feet from the store and the life cycle of that product is over and it gets tossed into the garbage. So all the way from raw resources to the disposal phase. That's sort of a hint as to what's going on in life cycle assessment or life cycle analysis. Okay, so you can use life cycle assessment to answer some pretty interesting questions. Like, for example, is a hybrid, in other words, an internal combustion electric car combination, better for the environment than a standard compact car? So, for example, a Toyota Prius versus a Honda Civic. And the Ontario government, it's been canceled by the Ford government, but until recently, the Ontario government was offering huge incentives for buying hybrids. And it's questionable because a hybrid car has a dual drivetrain, right? It has electric drivetrain and it has an internal combustion drivetrain and it has batteries which have their own environmental impacts. And so it may sound, is it really good for the environment? That's a question. We don't know. But the answer can be obtained through life cycle analysis or life cycle assessment. Another one you might worry about is, should you, if you have a restaurant, should you install electric hand dryer or should you have paper towels? Well, clearly that depends on how clean your electricity is. We've talked about that in Ontario. Electricity is clean. So it's a complicated question. The answer is not obvious. Another issue that I think I raised it in the photovoltaic section now, solar panels. So solar panels like this single cell panel here, does it take more energy to manufacture than it produces over its useful lifetime? Well, you should know the answer to that. I discussed it in that presentation. The answer is no. It takes about, if you're in a not very sunny location, it's 7 years, and then you can go down to as low as 3 years in a sunny location for a PV panel to pay back. And the lifetime of a PV panel is 30 years. But that's how you would answer that sort of question through life cycle assessment. Another sort of nasty rumor that's been circulating about nuclear energy is there's a huge amount of embodied energy. In other words, the energy required to build a nuclear plant. So you might ask, which requires more energy to manufacture, a wind turbine or a nuclear power plant in terms of kilowatt hours per kilowatt hour produced? And you could answer that with life cycle assessment. It turns out that nuclear has pretty low life cycle emissions. And so, yeah, life cycle assessment is a sort of a scientific methodology to answer these kind of questions that come up frequently, like paper or plastic in the grocery store, that sort of thing. So what is life cycle assessment? It's a holistic, cradle-to-grave estimation of the resource requirements and the environmental impacts of whatever you want to talk about, either a product, a process, a service, whatever you're interested in assessing environmentally. Now, what I'm presenting here is a bit technical. It's taken from an international standards organization standard. So there's a standard approach to doing a life cycle assessment. It comes from a ISO standard 14040. You can get it in the library. I put this here for my grad students. That's a bit more information than you need. But still, you might be interested. This is really sort of high-level environmental stuff, a life cycle assessment. You should have at least a sense of what's going on with this. Okay, so why would you do a life cycle assessment? Well, I just raised a bunch of questions that would be interesting to answer. And so it provides a framework for making sound environmental decisions. Not you should really think about whether you want to promote something before you provide a government incentive, for example, which is something the government is not always the best at doing. They should consult scientists and researchers who know about life cycle assessment. It's also a tool for eco design. I teach mechanical engineering, and we're really moving towards that. The idea that you want to think about the environmental impacts of your product during the design process and identify. You could take an existing product and identify places for improvement. I had a student who did a internship at Pratt and Whitney, and they were looking at ways they were doing life cycle analysis on their engines to see how they could improve their life cycle performance. How much well, it's not just carbon emissions, it's also acid rain and other impact categories. And so it's a big part for mechanical engineers. It's called design for environment, where you think about the environmental impacts over the entire life cycle, all the way from where the raw materials come from, all the way through use and disposal and manufacture and all that stuff. So you think about, what materials should I use? Can I use recycled materials? What manufacturing processes am I going to use? Which are the best for the environment? How should I package and ship? And how much does it use during the use phase, which is what we tend to focus on, but also disposal requirements. You think about all of that stuff up front using life cycle analysis. So we look at all the stages of a product's life, not just the use phase, which is what we tend to focus on. And so you would do that too for, as I've already mentioned this, rational government policy. Government should really base their incentive programs on whether it makes sense on a life cycle analysis, and for setting minimum standards. And one example is that California has this thing called the low carbon fuel standard, and it mandates that the fuel coming into their state has to have a 10% reduction in life cycle carbon intensity for the gasoline and diesel, compared to I've forgotten what the baseline year is, but that will block things like gasoline made from tar sands from California, because it has a high life cycle carbon emissions, because it takes a lot more energy to remove from the ground. You might also do it if you're a company for marketing reasons. You can definitely show that your product, if you do it through a careful life cycle analysis, you can show your product is definitely greener than your competitors, as opposed to greenwashing, which by greenwashing, I mean that marketing that promotes a misleading perception that either that your product is environmentally friendly. And there's lots of that out there. So it's a way to avoid a charge of greenwashing by doing a proper life cycle analysis. And there's lots of people who will do one for you nowadays. Okay, so what is the life cycle of a product? Well, you got to extract the raw materials. You have to process those materials. Then you have to manufacture your product. And then there's the use phase, the use of the product. It uses energy during that phase and has some emissions, like your car. And then there's this disposal phase. So it's that whole life cycle. And what life cycle analysis does, or life cyclist, it keeps track of the inputs and outputs for this whole thing. So I got a black box around here. It's going to look at the energy inputs, what kind of materials you require, how much water you use. And then the outputs are things like air pollution, water pollution, solid waste, heat coming out, which is not a big issue. You might use the heat as a co-product. You might use it to you cover some of that heat. Yeah, so energy recovery and co-products. What a co-product is, for example, let's think about this. Suppose you were a sawmill and you're making wood. You're sawing up logs and making planks. A co-product would be sawdust. You got sawdust, maybe you could turn that into wallboard. And so your output is not just bad things, but you could also have some positive co-products as well. So that's an example. So life cycle assessment considers that. And notice these arrows going back. Life cycle assessment considers the possibility that your product could be reused, remanufactured, or recycled. And I'll talk about those in the next slide. So reuse would be, an example would be how many times a plastic grocery bag might be reused. Remanufacture might be repair or refurbishing. I used to have a washing machine. There was a place where you could buy refurbished washing machines. So rather than throwing it out, a fellow would maybe replace the motor or something like that, and then resell the washing machine. And then there's recycling, which is kind of the last stage where an example of that would be when you throw out your, no, you don't throw it out in the landfill, but when you recycle a computer, they shred the circuit boards because they have uh, gold and some valuable metal content. And your car usually doesn't end up in the dump. It ends up being crushed and the steel gets recovered. So that's recycling of steel. So life cycle analysis considers the whole life cycle plus those possibilities that you could have reuse, remanufacture, and recycle. So all the inputs and outputs. This is a graphic taken from the ISO standard. Again, there's three main steps. One is you got a goal. Why are you doing it? What's the scope? I'll talk about that. Inventory analysis, that's actually figuring out all those gory details about what the inputs and outputs are. That's hard, although there's some software nowadays to do it. And then at the end, you want to look at impact assessment. What are the impact on climate change, air pollution, acid rain, stratospheric ozone depletion. There's a bunch of impact categories. That's why I put this at the end of the course, because now you should have at least a good overview of all those environmental impacts. People tend to think only about climate change nowadays. We're so focused on that. If you're looking at a product, you really should be looking at all the impact categories on the environment. I would say another one could even be, plastic going into the ocean. That's not even included in the standard, but so it's constantly evolving. And you'll see as we go, I'm going to talk about these steps. They're really kind of hard. There's a lot of interpretation, a lot of assumptions. It really requires judgment to do a good life cycle analysis. And there's some flaws. They're working on them. There's been some improvements in the life cycle analysis techniques because of, as I describe these steps, I think you'll see how hard a life cycle analysis can be. And how, if you're not honest, you can tailor the life cycle analysis to make your product look better than maybe it should. So there's a lot of interpretation involved. So let's go through the steps. The ISO standard says the first thing you should do is figure out what you're going to do. What's your goal and what's your scope? So you need to think about how you're going to apply the results of your life cycle analysis and your reason, because it affects some of your decisions that I'm going to talk about later on. So knowing why you're doing it helps establish the scope, and I'll talk about scope. The scope could include, it could be your product. You might be doing like Pratt & Whitney, looking at their engine and seeing how much carbon emissions or air pollution it emits over its life cycle. Or it could be comparative. You might be comparing to your competitor, or a classic one is paper versus plastic. When you go to the grocery store, do you get a paper bag or do you get a plastic bag? Which is worse for the environment? So you could be doing a comparative life cycle analysis. And if you're going to do that, you should be comparing on what's called the functional unit. It's defined in the standard. This is probably a bit more technical than necessary for MEC 110, but functional unit is a quantified performance of the system. So if you were, for example, comparing two types of insulation, like maybe styrofoam insulation versus, I don't know, what's the other one? Fiberglass insulation. If you were going to compare which one is better for the environment, you'd want to compare on a function basis. You want to compare a piece of styrofoam and a piece of fiberglass insulation that performs the same function, that has the same thermal resistance, same R value, provides the same insulation value. You wouldn't do it on a per mass basis. You wouldn't compare the 1 kilogram of styrofoam to 1 kilogram of fiberglass insulation. You'd take two things that perform the same function. For example, if you were trying to figure out an electric hand dryer was better than paper towels, let's suppose you did a little study and you found out that the average person uses 2 paper towels. So you'd compare 2 paper towels to the amount of electricity used to dry your hands. Maybe the average person uses, the blow dryer for 20 seconds at a certain power rate. And so you'd compare the things that perform the same function. That's called the functional unit. That's an important point in life cycle analysis. And then you want to look at the impact categories. And it's not just climate change. It's, as you learned, there's acid rain, so acid deposition, climate change, air pollution, ozone depletion, water pollution. There's many, many categories. Even I mentioned a new one that really isn't very well addressed, and that's plastic pollution in the ocean. Sort of how long a product persists in the environment, I think, is an interesting category. It's probably not captured well in life cycle analysis. You want to specify system boundaries. This is where I mentioned that it's hard to do a life cycle analysis. Think about this. Imagine if you were trying to figure out how much energy it took over the full life cycle to make a paper towel. And you're trying to figure out how much wood it takes and that sort of stuff. So trees are the raw material. But do you include the steel required, when they sawed the tree down, there was a saw involved. How much of the saw do you include? Do you include the lumberjack's lunch or the lumberjack's transportation to the place where he cut down the tree? So, there's kind of tendrils that go out from all of these products, and you have to saw it off at some point and say, I'm not going to include that. Those are called system boundaries. And if you're going to do a life cycle analysis, and if you're going to publish it, you have to clearly delineate those boundaries and why you chose those boundaries. And that's where you can, get into issues of, you can pick system boundaries that make your product maybe look a little bit better than maybe it is or should look. And after you've done all this, you've decided why you're doing it, what you're doing, what your boundary, how far you're going to go out on those tendrils. Then you look at the inventory analysis. That's the inputs and outputs. That's the raw materials, the energy, the products, co-products, the outputs to the air, the solid waste. Those are the inputs and outputs. That's super tedious. But there's nowadays, over the last couple of decades, there's been a number of software products that have available to do this. One is there's things like Gabby, Simpro. There's a BoostStep model. And I'm going to show you here, mechanical engineers use SolidWorks. SolidWorks has a life cycle assessment module. Let me just show it to you. It's kind of cool. Let me go back to pointer options. Okay, so I'm jumping out to a different presentation here. Yeah, so this is the SolidWorks lifecycle assessment. Again, it considers raw materials, materials processing, manufacturing, assembly, transportation, then the use phase, and then end of life, so disposal. It's all based on this ISO standard. And at each phase, they look at what the inputs are, inputs of energy and raw materials, and outputs to the environment, and possibly some co-products. And so it's all done in the software. So a mechanical engineer, for example, suppose they were going to design a gear. Here's a metal gear. And so you draw it in SolidWorks and you'd pick the material. And SolidWorks is kind of cool. It does stress analysis. So you can do something called finite element stress analysis. You can apply loads to the gear, and you can, this analysis has nothing to do with the environment. It's just about whether or not the gear would break, so you can size the teeth of so it doesn't break. Once you've done all that, SolidWorks, so this is an amazing design software for mechanical engineers. So once you've done all that, there's an additional tab in SolidWorks. And what you do is you click on this sustainability tab. You select what material this is. So in this case, it's aluminum, what the alloy is. You select what the manufacturing process is. And this is saying this is going to be milled, where it's going to be made. I've picked Asia, where it's coming to North America. And it runs this through the sustainability software, this inventory analysis, and it gives you the environmental impacts. So in each of the categories. So these are carbon emissions, and you can see yellow and blue. So for the raw material, for the transportation, for the manufacturing, and the end-of-life disposal. You can get carbon emissions, energy use, air pollution, and water pollution. And you can see I've done two here. You can go back and change this, and then you can get a comparison. So if I change this to a different material, or I change the manufacturing process, I can compare. So that's an example of the kind of sustainability software that's available now for mechanical engineers and for design, for eco-design. It's quite cool. It's all based on life cycle assessment. Okay, so that was the SolidWorks design software. Let me show you an example of inventory analysis just to see how complicated this gets. And this is why you need software for this. This is an inventory analysis, so inputs and outputs in terms of raw material and outputs for air pollution and water pollution for the just one stage, just the manufacturing stage of a PVC computer housing. So that's polyvinyl chloride computer housing. And so this is an example just of one stage of the manufacturing. So it's got the inputs in terms of crude oil, coal, natural gas, lignite, And the raw materials, bauxite, that's the ore of aluminum for aluminum, how much energy is required, how much water is required. And then the outputs would include the particulate matter, we have PM 2.5, carbon dioxide, carbon monoxide. You've learned about these in the air pollution part of the course, SOx and NOx. And then some of these are to do with water pollution and acid gases. You can see for the different phases of the manufacturing, it's really complicated. So you really want software to do that. And the Solidworks software does it. And there's a number of other software packages that will do that for different products. Just gives you an idea of how much goes into a life cycle analysis. Okay, and so once you've got your inputs and outputs, then you have to do this thing called life cycle impact assessment. And that's difficult, super difficult, all of these phases. So, the impact categories, it's not just climate change. It could be acid rain and air pollution. And so you have to think about all the different impact categories. I'm not going to go through this. This is more for my graduate course. This gets a little bit technical. But of course, for climate change, you use global warming potential. And if you had CO2 and methane, you would combine them together and do an equivalent using global warming potential. And of course, the environmental relevance is the radiative forcing, which is a proxy for the warming of the climate. And you'd look at the kilograms of CO2 equivalent per functional unit. So those are some of the fine details. But there's other impact categories beyond global warming. Those are the greenhouse gases, which you combine with global warming potential. There's stratospheric ozone depletion. I hope you've watched that. So nowadays we don't emit CFCs, but there are other possibilities, HCFCs and halons. There's acid rain from SOx and NOx, and there's water use and water pollution. So there's different impact categories, and you have to, it's really difficult because if you compare two products, one might be bad for the environment in global warming, and the other one might be bad for the environment in air pollution or acid rain. And it's really hard to you have to sort of decide which one is more important to you. And so a lot of times it's very difficult to tell which product is better because they usually have impacts in different categories. Let me show you a sample life cycle impact analysis for a solar panel. This is a solar PV panel. Yeah, this is from a paper in Energy 2008. It's looking at how much of the total impact on global warming. A PV panel emits 80 kilograms of CO2 equivalent over its life cycle, and this is telling you what fraction of it is associated with extraction and refining. Remember, solar panels are made of silicon dioxide, and they purify the silicon. And then, it goes through the different manufacturing processes, refining step 3 is transforming the silicon from metallurgical grade to solar grade, so really high purity. That's where a lot of the energy goes into refining that silica into a super pure before you can grow the crystals. And then it goes all the way up down here to a panel assembly. So that's the kind of details you get in a life cycle assessment. And I showed you this before. This is EPBT, is energy payback time. And here's this interesting table. So they used life cycle assessment to figure out that, they looked at how much energy it took to make a solar panel and how much energy you get back out. And in Ottawa, Canada, it takes about 4 years for the solar panel to pay back its energy. So the amount of energy coming out equals the amount of energy it took to manufacture the product. You could see in sunny places, where do we have somewhere sunny here? Portugal, Lisbon, Portugal, it's quite a bit lower. And less sunny places, it's longer. Okay, here's a very limited life cycle impact assessment for, it's kind of a famous one, paper versus styrofoam. If you go to the coffee shop, should you use of course you should use a reusable cup. Although that's, we'll talk about that. That's iffy too. Only if you don't lose the reusable cup every week. But presuming you have a long-lived reusable cup, you should use a reusable cup. But if you're using a disposable cup, would you or should you pick paper or styrofoam? Well, let's have a look at this. So these are kind of the impact categories for the life cycle assessment of a single-use hot drink cup. And the numbers in here are per 1,000 cups. So here we have the paper cup, and here we have the styrofoam cup, polyfoam cup. So just to show you how hard this is. So of course, the paper cup requires wood, 21 kilograms per 1,000 cups, and whereas the styrofoam cup requires oil. Styrofoam is made as it's a hydrocarbon product. So in terms of inputs, it's hard to judge those two. They're different categories. Okay, in terms of the energy used, well, they both use about the same energy to manufacture, but the paper cup uses more electricity. And you know, electricity is well, if it's not made right, if it's made with coal, it could have high impacts. So more energy used to make the paper cup than the styrofoam cup in terms of electricity. That's process heat, the other one. Yeah, it's about the same amount of thermal energy. Okay, and then a styrofoam cup is blown using pentane. It's a volatile organic compound. It's a blowing agent to expand the cup, and so that gets emitted to the environment. That's a air pollutant. And whereas the paper cup is made at a pulp and paper mill, and it has air pollution and water pollution, quite a bit of air pollution and water pollution. So it's probably a little bit worse on that score. And then when end of life, you can burn the paper cup. If you have a incinerator, you can recover some of the energy if that's available, and it gives up more energy than the styrofoam cup. So you can see that if you look at these, you're looking at different categories, and it's really, the winner is really quite hard to judge. So that gives you some concept of how hard life cycle assessment can be in terms of judging one product being better than another. You kind of have to decide what impact category, environmental impact, is more important, whether climate change is more important than, for example, water pollution. Okay, this is a really technical one. This is from my grad course. So this is some results of looking at the life cycle analysis of, as an example, of the Sheppard Young subway. So this is the new subway line, line 4, 5.5 kilometers long. And there was a journal paper published here by Sachs and Miller and Guthrie looking at the net greenhouse gas impacts of this Sheppard subway line. So it's pretty new. It's an interesting example of life cycle analysis. So they looked at, of course, all the emissions that went into digging the subway, processing the raw materials, construction, and operation. They looked at the emissions offset during the use phase because people are not using their cars. Of course, that's the whole idea, is to get people in the subway, so they use the subway and they don't drive their cars. And they looked at the emissions reductions, because housing would become more dense along the subway line, because it's a very desirable place to live. You can get on access to the city through the subway. And so they looked at the emissions associated with housing becoming denser and more people using the subway. So here's the result. Kind of interesting. The mean payback time. They looked at sort of optimistic and pessimistic assumptions, and somewhere in the middle was it takes about 23 years for this subway to pay back the CO2 emissions that it took to make it. It turns out that subways have a huge front end load of emissions compared to other options like streetcars and light rail. So these are the kind of things that I'm sure that the Ford government is not as well up on as perhaps they should be. So yeah, governments really need to look at these kind of analyses carefully in thinking about guiding infrastructure decisions to make greenhouse gas targets. If you're talking about even the mid-range being 23 years to pay back CO2, that's quite a long target. That's the actual cover of the paper, net greenhouse gas emissions. And yeah, so they optimistically, greenhouse gas payback takes somewhere between 11 and 35 years, depending on whether you take optimistic assumptions and pessimistic assumptions. And then there's this little thing down here. It says, payback period is very sensitive to the potential for induced demand to backfill the mode-shifted automobile kilometers. Oh, don't you love how academics talk in gobbledygook? Well, if you read the paper carefully, what that means, and I'll tell you what it means, is that when you build a subway, you get people off the roads, you get them into the subway. That's the purpose. But that makes the roads less busy for a little while and less congestion. And guess what happens? People like quiet roads, so car travel becomes more effective, and there's a certain backfill of that. You've moved people off the roads, but new people come and fill up the traffic. So there's some backfill. And so if you assume some significant backfill, you might even get up to 35 years before the CO2 emissions from building a subway from that subway are paid back. So that gives you some idea. I think that's a pretty interesting topic. It's an area of research. It's the kind of thing you could probably do a master's or PhD on if you're interested in that sort of thing. And that completes the presentation and all of the video lectures in this course. I hope you enjoyed it. Bye for now. Good luck with exams.